Welcome back. Last episode, we learned to see a matrix as a motion of space. It rotates, stretches, shears, and reflects every vector you feed it. For a typical vector, the matrix does two things at once. It changes how long the vector is, and it swings it around to point in a new direction. But here is the surprise that powers the rest of this course. For almost every matrix, there are a few rare directions that the matrix simply refuses to turn. A vector pointing along one of those directions comes out pointing the exact same way, only longer or shorter. Those special vectors are called eigenvectors, and the factor by which each one is stretched is its eigenvalue. The whole idea lives in one short equation, a times b equals lambda times v. Today, we will unpack that equation, see its geometry, meet the eigenspaces, and learn how to find eigenvectors by hand. By the end, you will look at a matrix and see, not a grid of numbers, but a set of stretching axes. Let's pin down the definition. A non-zero vector v is called an eigenvector of a square matrix A if applying a to v just scales it, a times v equals lambda times v, where lambda is some number called the eigenvalue. Stare at the two sides of this equation because the contrast is the whole point. On the left, the matrix A transforms the vector v in its full complicated way, mixing components, rotating, stretching. On the right, all that machinery collapses into a single multiplication, v simply scaled by the number lambda. For this one special vector, the entire matrix behaves like a humble scalar. One technical condition, the eigenvector must be non-zero. Why? Because if you allowed the zero vector, the equation a times 0 equals lambda times 0 would hold for every possible lambda. It tells you nothing. So we ban the zero vector as an eigenvector. But be careful, the eigenvalue lambda itself is perfectly allowed to be 0. A zero eigenvalue means the matrix crushes that direction down to nothing, which is genuinely informative. Here is the simplest skill of all, checking whether a vector you are handed is an eigenvector. You don't need any theory, just multiply and compare. If the output a times v is a scalar multiple of v itself, then v is an eigenvector, and that scalar is its eigenvalue. If the output points in a genuinely new direction, it is not. Let's try it. Take the matrix with 2, 1 on top and 1, 2 on the bottom, and test the vector 1, 1. Multiply. The first component is 2 plus 1, which is 3. The second is 1 plus 2, also 3. So the output is 3, 3, which is exactly 3 times the original vector 1, 1. It passed. 1, 1 is an eigenvector with eigenvalue 3. Now test a different candidate, the vector 1, 0. Multiplying gives 2, 1. Is 2, 1 a multiple of 1, 0? No. The second component went from 0 to 1, so the direction changed. So 1, 0 is not an eigenvector of this matrix. That is the entire test, multiply, and ask whether you landed back on the same line. Now the geometry, which is where eigenvectors become unforgettable. Imagine the matrix A acting on every vector in the plane at once. Take a generic vector x. When you apply a, the output a times x points in a new direction. It has been swung around to a different heading. That is the normal behavior almost every vector gets rotated. But take an eigenvector v. When you apply a, the output a times b lies along the very same line that v did. It did not turn at all. It only grew longer, or shrank, or flipped end for end. So an eigenvector marks an invariant axis, a line to the origin that the matrix maps right back onto itself. The eigenvalue tells you exactly what happens along that axis. If lambda is bigger than 1, the axis stretches outward. If lambda is between 0 and 1, it shrinks toward the origin. If lambda equals 1, vectors on that axis are frozen in place. If lambda is negative, the vector flips to the opposite ray and then scales. And if lambda is 0, the whole axis collapses onto the origin. Eigenvectors never come alone. If v is an eigenvector for the eigenvalue lambda, then so is any non-zero scalar multiple of v. Here is the quick check, apply a to c times v. By linearity, you can pull the c out front, giving c times av, which is c times lambda v, which rearranges to lambda times cv. So c times v satisfies the same eigenvalue equation. That makes sense geometrically. The whole invariant axis stretches by the same factor, not just one arrow on it. So for each eigenvalue, the eigenvectors fill out an entire line or sometimes an entire plane. We collect them, throw in the zero vector to round things off, and call the result the eigenspace of lambda. The eigenspace is genuinely a subspace. It contains the origin and is closed under addition and scaling. And here is a clean description we will use constantly. The eigenspace of lambda is exactly the null space, or kernel, of the matrix A minus lambda times the identity. The dimension of that eigenspace is called the geometric multiplicity of lambda. How many independent directions share the same stretch factor? Before we compute, let's say why anyone cares about these special directions, because the payoff is enormous. The first reason is decoupling. Along the eigenaxis, the matrix acts on each direction completely independently, one simple scalar stretch at a time. A motion that looked tangled and complicated, mixing all the components together, becomes a handful of separate, easy stretches once you look along the right axis. The second reason is powers. If you apply the matrix again and again to an eigenvector, each application just multiplies by lambda, so applying it k times multiplies by lambda to the k. Computing high powers of a matrix, which is normally brutal, becomes trivial on an eigenvector, and that is the engine behind Markov chains and dynamical systems. The third reason is diagonalization, which we tackle in the coming episodes. In a basis made of eigenvectors, the matrix looks perfectly diagonal. And the fourth reason is physics. Vibration modes, principal axes of rotation, quantum states are all eigenvectors. Find the eigenaxes, and the matrix stops being a grid of numbers and becomes a few simple stretches. Now suppose someone hands you an eigenvalue lambda and asks you to find the eigenvectors that go with it. Here is the mechanical recipe. Start from the eigenvalue equation, a times v equals lambda times v, and move everything to one side, a times v minus lambda times v equals the 0 vector. We would like to factor out v, but there is a subtlety. You cannot subtract the scalar lambda from the matrix A directly, because one is a number and the other is a grid. The fix is to insert the identity matrix. Lambda times v is the same as lambda times the identity times b. Now we can factor cleanly and get the matrix A minus lambda times the identity, acting on v, equals the 0 vector. So the recipe is, form the matrix A minus lambda I, then find its null space by solving that homogeneous system. Every non-zero solution is an eigenvector, and the whole null space is the eigenspace. And here is the guarantee that makes it work, because lambda is a genuine eigenvalue. The matrix A minus lambda I is singular, so it must have non-zero vectors in its null space. There is always something to find. This figure is the one to remember. We have a single grid centered at the origin, and we apply one matrix to a whole fan of vectors. Look at the thin gray arrows first. They fan out in every direction like spokes of a wheel, and each one has a little curved arrow showing how the matrix swings it to a new angle. That is the generic story. Feed the matrix an ordinary vector and it gets turned. Now look at the two bold colored lines through the origin. Along the gold line, the input eigenvector and its output both lie on the same straight line. The matrix did not turn it one bit, it only stretched it to twice its length. That's an eigenvalue of 2. Along the teal line, the same thing happens, but the output is shorter than the input. The matrix shrank it to half its length. That is an eigenvalue of 1/2. The contrast is the whole concept on one canvas. Gray vectors swing to new directions while the eigendirections hold their line and merely change length. Find those lines and you have found the skeleton of the matrix. Before the worked examples, an honest warning. Not every real matrix has real eigenvectors. Take a pure rotation by 90 degrees with matrix 0, -1 on top and 1, 0 on the bottom. Ask the eigen question, is there any line through the origin that this rotation leaves in place? Think about physically spinning the whole plane a quarter turn. Every single direction moves to a new direction. There is no axis that stays put. So a pure rotation has no real eigenvectors at all. There is no non-zero real vector that comes out pointing the same way. This is not a failure, it is information. What happens is that the eigenvalues turn out to be complex numbers, in this case I and -I, the imaginary units. Complex eigenvalues are the algebraic fingerprint of rotation. Whenever you compute eigenvalues and they come out complex, the matrix is doing some spinning. We will see how to actually compute these complex values next episode using the characteristic equation, and then devote a whole later episode to what they mean. For now, just hold the idea. Rotation hides its eigenvalues in the complex numbers. Let's start with the easiest possible case to build intuition. Take the diagonal matrix with 3 and 2 on its diagonal. What does it do to the first basis vector? 1, 0. Multiplying gives 3, 0, which is exactly 3 times the original vector. So 1, 0 is an eigenvector with eigenvalue 3. The x-axis stretches by a factor of 3. Now the second basis vector 0, 1. Multiplying gives 0, 2, which is 2 times the original. So 0, 1 is an eigenvector with eigenvalue 2. The y-axis stretches by a factor of 2. No rotation, just 2 independent stretches along the coordinate axes. This is the cleanest situation in all of linear algebra. A diagonal matrix simply wears its eigenvalues right on the diagonal, and its eigenvectors are the coordinate axes themselves. A huge amount of what we do in the coming episodes is about trying to make other matrices look diagonal by finding the right axes, and those right axes are exactly the eigenvectors. Now a more geometric example, reflection across the x-axis, whose matrix has 1 and -1 on the diagonal. Think about what reflection does before computing anything. Vectors lying right on the mirror, the x-axis, don't move at all when you reflect. Let's confirm, apply a to 1, 0, and you get back 1, 0, which is plus 1 times the original. So the mirror direction is an eigenvector with eigenvalue 1. Points on the mirror are fixed. Now think about vectors perpendicular to the mirror along the y-axis. Reflection flips them straight across to the other side. Apply a to 0, 1, and you get 0, negative 1, which is negative 1 times the original. So the perpendicular direction is an eigenvector with eigenvalue negative 1. The vector flipped n for n without changing length. This pattern holds for every reflection in the plane. There are always two eigendirections, the mirror line with eigenvalue plus 1, and the direction perpendicular to it with eigenvalue negative 1. The eigenvalues encode the geometry exactly. For our last example, let's actually run the recipe and find an eigenspace. Take the horizontal shear with 1, 1 on the top row, and 0, 1 on the bottom. I'll tell you that lambda equals 1 is an eigenvalue and ask you to find its eigenvectors. Step 1. Form the matrix A minus 1 times the identity. Subtracting 1 from each diagonal entry gives a matrix with 0, 1 on top, and 0, 0 on the bottom. Step 2. Find its null space. Multiply that matrix by a general vector xy and you get the vector y, 0. Setting this equal to the 0 vector forces y to be 0 while x is free to be anything. So the eigenspace is all vectors of the form x, 0, that is the x-axis, and only the x-axis. This is the interesting twist about a shear. It has just a single eigendirection, the horizontal axis it leaves fixed. Every other vector in the plane genuinely gets tilted by the shear, knocked off its original line, so it is not an eigenvector at all. Some matrices are generous with eigendirections. A shear is stingy, giving up exactly 1. Let's gather our three examples into one comparison picture. On the left is the diagonal scaling matrix. It has two eigenlines, the x-axis, stretched by a factor of 3, and the y-axis, stretched by a factor of 2. Two independent stretch axes, both standing still in direction. In the middle is the reflection. Its eigenlines are the mirror, the x-axis, with eigenvalue plus 1. A vector there sits perfectly still, and the perpendicular y-axis, with eigenvalue negative 1, where you can see the input arrow pointing up and its output arrow flipped to point down along the same vertical line. On the right is the shear, the stingy one. It has only a single eigenline, the x-axis, with eigenvalue 1, and we show a faint generic vector getting tilted off its line by the shear to remind you that no second eigendirection exists. Three matrices, three very different eigenportraits. Reading a matrix by its eigenlines is like reading a face by its bones. The lines tell you what kind of motion the matrix really is. A little history, because the name itself has a story. The idea is old. In the 1700s, Euler and Lagrange studied the principal axes of rotating bodies and of quadratic forms. These were eigenvectors in all but name, the special directions along which a physical system behaves simply. In the 1820s and 30s, Augustin Louis Cauchy made the theory rigorous, proving that real symmetric systems always have real principal values, and laying down what we now call spectral theory. The modern word arrived around 1904 with David Hilbert, who coined the German term eigenwert. The prefix eigen is German for own or characteristic, so an eigenvalue is the matrix's own characteristic value, the stretching factor that belongs to it intrinsically. Over the 20th century, the hybrid words eigenvalue and eigenvector became standard English, half German and half English, and they became absolutely central to physics. In quantum mechanics, the measurable quantities of nature, energy, momentum, spin, are literally the eigenvalues of operators. The math we are doing is the grammar of the physical world. Let's recap. The defining equation is A times V equals lambda times V, with V a non-zero vector. The matrix A acts on the eigenvector V by simply scaling it by the eigenvalue lambda. Geometrically, an eigenvector marks an invariant axis, a direction the matrix only stretches and never rotates, while almost every other vector gets swung to a new heading. The eigenvalue lambda is the stretch factor, and it is free to be negative, which flips the direction, or even 0, which collapses it. For each eigenvalue, the eigenvectors fill out a subspace called the eigenspace, which is exactly the null space of A minus lambda times the identity, and its dimension is the geometric multiplicity. To find eigenvectors once you know an eigenvalue, you solve the homogeneous system A minus lambda I times B equals 0. We saw three examples: a diagonal matrix whose eigenvectors are the coordinate axes, a reflection with eigenvalues plus 1 and minus 1, and a shear with a single eigendirection. Next episode, the missing piece: how to find the eigenvalues themselves from the determinant of A minus lambda I. Today we met the eigenvectors and eigenvalues of a matrix. The central equation is A times V equals lambda times V. It says that when the matrix A acts on a special vector v, the result is just v scaled by the number lambda, same direction, only stretched or shrunk. The vector v is called an eigenvector, and the scaling factor lambda is its eigenvalue. Geometrically, eigenvectors are the directions the matrix only stretches and never rotates. Almost every other vector gets swung to a new heading. We saw that for a fixed eigenvalue, all of its eigenvectors, together with the zero vector, form a subspace called the eigenspace. And we learned the recipe. Once you know an eigenvalue lambda, you find its eigenvectors by solving the system A minus lambda times the identity, all acting on v equals 0. That is, you find the null space of A minus lambda I. We worked through simple 2x2 examples, including a shear that has only one eigendirection and a reflection whose eigenvalues are +1 and -1. Next episode, we close the loop and learn how to find the eigenvalues in the first place, using the characteristic equation, the determinant of A minus lambda I set equal to 0. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.